The idea behind covalent bonds is instead of giving up electrons or gaining electrons, two atoms will come together and just share electrons. The idea of sharing is so that as they share electrons, they can form octets in their valence electron shells. They want to have at least eight electrons in that last valence electron shell. And so that is the ideal situation that they hope for. The way this happens, it's not just an electron like hanging out in between two atoms. What it really is an overlap of shared electron clouds. And then that overlap of electron clouds will be the source of the attraction between the two nuclei. Normally, atoms within covalent compounds are typically electrically neutral, or at least they're very close to it. So here's an idea, an image of what a covalent bond might look like. In the top figure here, we have two hydrogen atoms. The nucleus is positively charged, +1, because the nucleus is one proton, that's all it is. Then you have the blue region, which is the electron cloud around each hydrogen. As they get closer together, the electron clouds overlap, and as such, basically an electron from one atom can serve to balance the valence shell for the second atom as well. And so this particular bond is what we call a hydrogen bond. It's a particularly strong form of the covalent bond. The way we would write this bond is either, say, we put a colon in between the two H's, or more commonly, we say H-H, the dash indicating that there is a pair of shared electrons between the two hydrogen atoms. Now, it's kind of cumbersome to use this electron cloud imagery every time we want to indicate a covalent bond. So we use the electron dot representation, which is just using writing out the number of electrons in the valence shell by dots. So for instance, a chlorine atom has 7 valence electrons, so it has 7 dots around it. Now, in this case, you have 2 chlorine atoms. Both have 7. Each of them wants 1 more electron. So they say, hey, we both want an electron, let's share. And so right in the middle, you can see they kind of come together, and those 2 electrons are shared between the 2 chlorine atoms. This is what we call a bonding pair. All the others are lone pairs, meaning those are pairs of electrons that stay with a particular atom. But the bonding pair kind of bonds between the 2 different atoms together. Now, it is possible to share more than 1 pair of electrons. Here are a couple of examples. On the left, we have ethylene. You have 2 carbon atoms. Carbon has 4 valence electrons. And you have 4 hydrogens, which has 1 valence electron. Now, that means hydrogen has 4 to share with the 2 carbons, which need a total of 8 between the 2 of them. It's not going to work. So what happens is carbon is going to share 2 of each atom's electrons, 2 electrons from each atom, there we go, which leaves 2 electrons from that are not paired. And so you take 2 hydrogens, put them with 1 atom, and then the other 2 hydrogens with the other atom, and that gives you a total of 4 from the bond, the covalent bond between the carbons, plus 2 from the carbon atom itself, plus 2 more from the hydrogen atom. So we would write it like this. You have 2 carbon atoms. Since we have 2 pairs of shared electrons, we have two lines in the middle. We call this a double bond, meaning each line represents two electrons. So you're going to have 2, 4, 6, 8 electrons around the carbon. And that is what you need. We've formed our octet, and the same with the other carbon atom. Just remember that hydrogen, since it's in the first row, it's in the first energy level, you only have a 1s electron shell, which means you can only have 2 electrons at most. So one bonding pair is all you need for hydrogen. Acetylene is another example. Again, you have 2 carbon atoms with 4 valence electrons, but this time you only have 2 hydrogens. Well, if you put 1 hydrogen with each carbon, that gives you 1 more electron, so 5 electrons for each carbon. We still need 3 more. So we're going to take the 3 from this carbon and the 3 from this carbon and share them. So there are 3 pairs of shared electrons. Those 3 pairs of shared electrons would create what we call a triple bond. And then you have your 1 bond with the carbon and hydrogen. Let's take a look at some compound formulas. Now, the number of covalent bonds in an atom are determined by the number of valence electrons. For example, hydrogen has 1 valence electron, and so you can only have a single bond. That's it, just a single bond. Oxygen, on the other hand, has two valence electrons, or rather, it has room to accept 2 more electrons. That's the better way to say it. And so you can either have 2 single bonds or 1 double bond. That's what's possible with oxygen because it can accept 2 more valence electrons. Nitrogen can accept 3 more valence electrons, which means you can either have 3 triple bonds, 3 single bonds, a single bond and a double bond, or a triple bond. It would work in any case for nitrogen. Carbon was what we saw in the last slide. There are 4 valence electrons, which means it can accept 4 more. Carbon is the same way. You can have 4 different arrangements, all single bonds, a combination of single and double, 2 double bonds, or a single and a triple. So you can have combinations of single, double, and triple bonds. Now, just as a note, single bonds are quite strong. Double bonds are even stronger. Triple bonds are the strongest bond there is. Now, just as an example, if you look at the composition of the Earth's atmosphere, you'll see that the Earth's atmosphere is primarily nitrogen. About 78% of the Earth's atmosphere is nitrogen. The reason for this is that we saw that nitrogen can form triple bonds. Well, if it forms a triple bond with another nitrogen, then that atom is very, very difficult to break apart. So once it's introduced in the atmosphere, it stays. And so there is a lot of this nitrogen compound in our atmosphere. That's just an example, not a critical point, just an example of the triple bond. Here's another example. You have carbon dioxide and carbon tetrachloride. You can see that carbon, in both cases, there are 4 bonds around the carbon. In the case of carbon dioxide, you have 2 double bonds, but carbon tetrachloride, you have 4 single bonds. To name a covalent compound, it's very similar to it's quite different from the ionic compounds. Ionic, you have a metal and a nonmetal, but covalent compounds are just nonmetals. The way we name compounds is you generally have 2 elements. The first element, you give its name with a Greek prefix indicating the number of atoms in the compound. The Greek prefix is this first column of the table. Mono meaning 1, di meaning 2, tri meaning 3, tetra 4, and so on. And then for the second element in the compound, you use the stem name. The stem name is indicated by this last column. So hydrogen, you would use hydro. Carbon, you use carb. Nitrogen, nitro. Oxygen, ox, so on. And then and then you also have to include a Greek prefix number as well for that. And then you end with "-ide" if it's just two elements in the compound. Now, let's do an example, one that everybody knows, H2O, also known as water. So the first thing we do is take the first element with a Greek prefix. So we have 2 hydrogen atoms. The prefix for 2 is di, and then we put in the name hydrogen. That's the first element. The second name, we use a stem. It's oxygen, so we're going to use the stem name ox, and then end with IDE for a compound with just 2 elements. So the official covalent compound name for water is dihydrogen. Oh, I forgot something here. I apologize. Let me go back because we wanted the Greek prefix number as well. It's 1 oxygen, 1 meaning mono. Oxygen, we use the stem name ox, mon ox, and then end with ide. Dihydrogen meaning 2 hydrogens, mon-ox meaning 1 oxygen, and then ide being the end of the compound name. So that would be the official name for water, dihydrogen monoxide.